physics part of it as well, because that is where we can design efficient mixers. Okay? Right. So using these various mixers, we do have formulations. We have lots of formulation that we do before, and also we have some of them go towards the clinical trial, maybe first stage and things like that. However, the interesting part of this is that what what we can manage or what we can modify between one formulation to another, not only the composition of the formulation, which is the lipids, but also the flow rate ratio and the total flow rate. So the flow rate ratio is talking about how much aqueous lipid will be put, aqueous phase will be put in compared to the lipid phase, and also the total flow rate, which is how much liquid will be passed through the mixers at any given time. Okay, so from this architecture, we can see that lots of formulation and lots of entrapped material and lots of loading as well. Okay, uh, we can see that once we have at the end of the process, we have a completed product. Now this process is very fast. Micro mixer, all of this thing, it takes less than 20 seconds. You just put it in, you just press everything in, and then at the end of it, you get all the liposomes you want. Well, albeit it's an unpurified liposome still. However, it is much faster, and it is much more reliable compared to thin film hydration and so on and so forth. Okay? Because we can control the parameters of the manufacturing. Right? So advantages is consistent, controllable throughput via manipulation of quantifiable parameters, I mentioned before, and works on a wide range of APIs. We do have lots of API that we can try with these microfluidics. As I mentioned before, we can also go for small molecules like doxorubicin and amphotericin, all the way to mRNA, because it works like that. Now, the issue with other methods of formulation, other methods of manufacturing, is that you might have to introduce a very corrosive solvent, or you might have to introduce a very high temperature, which is not suitable for certain proteins and mRNA, for example. Okay? So inline process temperature is adjustable. So for some product that do require high temperature, you can attach heater to this microfluidic system in order to get a specific temperature that you want, and directly scalable from lab to mass GMP level production. Way back when I worked in University of Strathclyde, Glasgow, so I work with CMAC, continuous manufacturing and crystallization. So they do have collaboration with Cancer Research UK. So my research is specifically on the combination of two drugs within one liposome. So you know that we do have therapy, cancer therapy, which require combination of drugs, right? So instead of giving these drugs by cycles, we can give it together. So when giving it together, because it works synergistically, therefore the effect on the cancer cell is much more compared to individual given. This is compared to even if we give the naked drug without the liposomes together within the same composition as well. So we can see that using the liposome as the carrier and using the combination and using this method as well, we can produce a consistently similar product with the same composition of the drug inside them. Okay, so back when in Strathclyde, I used the benchtop one. It's a very small one. It's about this height. Okay, so basically, uh, you have to have some syringe. You syringe in all your aqueous and lipid phase, and then you put in machine, and then it will press the syringe, and the liposome will come out. So that is per batch. So one batch you can get maybe like 15 to 20 mil of liposome, for example. Then from there, I brought my formulation. I went to University of Vancouver in Canada, so British Columbia in Vancouver, Canada. So there they have the company that made this precision on the system. So this is GMP level manufacturing in microfluidics. So they no longer use the syringe. They can pump directly towards the chip itself, the lab on chip itself, and they are not using staggered herringbone mixer, but instead they use toroidal mixer in order for them to have a consistent and continuous production. So this can produce 5 liters, 10 liters per batch easily. Okay, so now there are some engineering consideration as well when you are thinking about this. For example, This is some trivia that I think if you really like going to microfluidics, you have to think about this as well. For example, when you use syringe to introduce your aqueous and lipid phase into the microfluidics, you have to be careful that each step of the pushing of the syringe, of the plunger into the syringe, it has to be smooth movement. Otherwise, you will introduce turbulent flow by stepping it up. So the engineers in precision nano system, they have to create a specific motor for this in order to have the pushing of the syringe as smooth as possible. Similar, it goes to this system, which it doesn't use syringe, it uses pump. However, pumping also creates a turbulent flow. It has ebb and tide. It's like, for example, it has a one part. For example, if you use peristaltic pump, it has one part where the pressure is higher and then the pressure is lower again. The pressure is not consistent throughout the flow of the system, but it has ebb and flow like that. So basically, you have to make sure that the pumping of the liquid and everything has to be consistent throughout the system. So it is a bit of engineering trick as well, where you have to learn about it and understand why they make the system like this. Okay? But most importantly, it is directly scalable from lab to mass GMP level formulation, which I use the same formulation in the benchtop, and then I use in this machine, I get the same result. Okay, and also it is open-ended process suitable for continuous manufacturing. This I will explain later. Okay, so this is the one that I get from transferring the directly the one from the benchtop, from the lab scale directly to the GMP scale. So for example, you can look at the on the graph on the left there. Okay, so this one I loaded it with pyranine. So at zero pyranine concentration, it is the same size. It is exactly the same size. So you go further, you load pyranine and everything. The variation in the size itself, however, for some of it, it might be significant. For example, it has a difference of 2 or 3 nanometers, but in larger sense of scale, 2 or 3 nanometers for liposome is not that different. You have to make sure that it doesn't go towards like further away from your target size. For example, if you want to do the cell uptake, it has to be within 90 to 200. So it has to be within that range. If it's go further than that range, then it is not directly scalable from benchtop all the way to GMP. Okay, right. So on the research trend on liposomes, okay, if you look at here, right, earlier, we can see that almost, not almost, more like 80 years before, 1945 to 1960, all people are talking about liposomes, just liposome itself, okay? So liposome publication is a lot. However, only in recent years, we start talking about self-assembled liposome, and also we start talking about microfluidics technology. Because as I mentioned before, everyone wants to do liposome. Everyone wants to encapsulate something into something. So that is what everyone wants to do. However, if you look towards what you research, okay, you have to understand that the knowledge has to be shared. It has to benefit the humankind. I believe in IUM, what we do is the technology that benefit the humankind. We have to have a technology that not only for us to publish, not only for us to put in the rack, but the technology has to be applicable and the technology has to be affordable as well. So strong trend of research on mass scale liposome manufacturing only emerged in years, okay? But fueled partly by the success of COVID vaccines such as Pfizer BioNTech Germany. So people can see that, oh, this works. We can load the mRNA into the liposome. But this has been done before. People has did this loading the mRNA into the liposome since forever, since even before COVID, 10 years, 1 decade before that. However, what Pfizer and BioNTech did was to show that it is possible to create this at mass scale, to create this so that it is affordable and it can achieve economies of scale. Okay, so next one, I will talk about tangential flow filtration. This is a supplementary to what we can have in terms of continuous manufacturing of liposome. So remember that I said about the microfluidics is open-ended. So by the end of it, it's not that you collect the liposome within whatever reactor or whatever flask that you made. It is basically an open-ended. You have an output, and that output can be connected together to this filtration. Now, what we do in lab usually, okay, for filtration, for purification of liposome, we can do ultracentrifugation, we can do filter centrifugation, we can do dialysis. However, these are close-ended. Basically, you put it in centrifuge, you run it, and then you take it out. Same thing with dialysis. You put in dialysis bag, you put in the sink condition, and then after a certain time, you change the sink, buffer sink and everything, and then you take it out. So it is close-ended. You cannot connect it to another system. However, in this system, okay, basically, you can connect it to another system. What I can show you here, for example, the feed there can be connected to the microfluidic system, and then we adjust the pressure within the system so that whatever that is not incorporated within the liposome, whether it is the API or the lipid itself, will be filtered out, so it will go out through the filtrate. Now it doesn't clog the filter because it is tangential. If it is parallel, basically directly towards the filter, then the filter will get clogged. But this one is tangential. The pressure is not directly towards the filter itself, so it doesn't get clogged. So at the end of the day, what you can have is not only a purified liposome, but also you can concentrate the liposome itself. So you can adjust the concentration of liposomes, and by the end of it, you have purified and also concentrate, and also you can adjust how much you can put into each vial. And this product is scalable. Okay, so for example, okay, you can see this machine. Okay, this you have a one cassette of tangential flow filtration. You can see the liquid coming from the top, okay, and then liquid coming from the bottom. The one is being pumped into the system, and then the one you have a small aperture there to induce pressure inside the system so that the filtrate can come out to the beaker next to the pump itself. Okay, so now this cassette, the more that you have it, the more that you run the fluid, the liposome solution within the system, the larger the area of filtration. So the larger the area of filtration, the faster you can purify, and also you can concentrate your liposome formulation. So it enables continuous manufacturing process, as mentioned. You can directly take the microfluidics, you can connect it directly to the tangential flow filtration, and it's modular to suit purification and concentration process. So by the end of this process, you can have within that jar there on the left a purified and concentrated liposome formulation, and also it's not destructive to liposome. The problem with ultrafiltration and also centrifugation, filter centrifugation, for example, some of these liposome, they might get stuck into the filter. They might get, if you do ultracentrifugation, the compressed effect on the liposome itself might alter the size, might alter the PDI and everything. So that is also a problem. Minimal losses to that volume within equipment because you can flush this away, and it can also handle large volume of product. As I mentioned, this is modular. The more you add the cassette there, the more you add the modules, the larger the surface area and the larger volume that it can handle at one run. So you don't need to run it again and again and again. And also you can actually flush. You can actually flush this thing. Basically, if you can see the jar on the left, at the top there, you can see the two connectors, but actually there is one other connector that can go into the jar. That one is for fresh buffer. You can put into that again. Basically, what will happen is that once the liposome itself has been filtered out, okay, and then it goes back into this jar, and then it will create the pressure inside. Because basically, once you take out the retentate, okay, the filter has been taken out, the amount of volume inside the jar itself will be lessened. Therefore, it creates negative pressure and will take out more fresh buffer inside that. So you can run the process again and again and again to ensure that it is continuously purified. At the end of the day, you can get a purified liposome, and also you can concentrate it as well. Okay, so that's the advantage of this. Now, for the conclusion. Okay, these are just two things that I want to show you guys. But what I see an opportunity here within the region, within the Asian region. Okay, we are blessed actually with lots of natural resources. We have lots of plants. We have lots of herbs. We have lots of lots of resources that we have around us. Okay, I would like to think that because we live in tropical countries, if you go to colder countries, for example, UK, for example, right, there are cycles of life. Basically, what happen is every autumn, every winter, everything will die, and then it will restart back again during spring and during summer. So there's not enough time for microorganism, for plants, for animals to create things, to produce metabolites, to produce lots of chemicals to protect themselves or others. But here within our region, we are sunny all year round. So basically, we do have things are growing all year round. So basically, we have lots of things growing, and we have lots of metabolites from plants and everything. So these kind of resources that we keep every year, we publish things that we encapsulate inside liposomes and everything. They are good. However, what we have to think moving forward is we have to make sure that this liposomal product has a chance to move from lab to a higher level of production. Because if you want to move to clinical trial, you have to have a certain amount, because you have to administer this to a certain number of subjects. If you can just have for per batch, for example, maybe like 3 patients, and then that's it, you have to do another batch, and then you have to see whether there are variation from batch to batch. There are lots of work, and mostly people don't do this work. All of these liposomal products and everything that we do in our lab, they just, be written, and then we just put in rack, and then we forget about it. Okay. So I hope that moving forward, we can work together. We can see where we can go with this technology. And hopefully in the future, we can see that more nanoparticle products can reach the market, and we can be proud of it because it is our work, and it can be beneficial to Ummah, to the humankind, inshallah. So I think that's all for me. Thank you very much.
Okay. I think okay. Thank you, Dr. Ted, for your really nice presentation. That's well, unfortunately, I'm not a nanoparticle one. But of course, we have like a great relation with the nanoparticle something because I work with the natural product, and I'm sure that some natural product can be converted or become a nanoparticle. But this is a really, really interesting topic actually because it's how to use the technology for the nanoparticle to solve the problem. Actually, that's what I know. Yeah, because usually with the some preparation there is some problem, so we use as a nanoparticle as a kind of an answer for solving problem. Okay. Okay. Now we are going to open the Q&A session. So, is there any question? Yeah. Okay. Lambang first. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Salam. Yeah.
Thank you for your presentation. You presented about the quite. It's very interesting because maybe to month ago, I found this technique I do something. Looking up paper about the mathematics, and then you describe about the mathematics. Maybe I will asking for you because I think you have experience of this type for your research. The first is how to optimize the type of chip because microbiology have type of chip type for the process nanoparticle fabrication. How to choose and optimize what type of chip. Second is how to control and the and optimization for microbiology and using liposome. As you know, liposome many techniques, right? Lipid degradation, direct injection, maybe, or
uh, others, filtration maybe, filtration, uh, because the system is quite challenging, right? We using lipid, and not only one, maybe we combine for drug delivery, especially for targeted drug delivery. We using lipid conjunction with AG, or we conjunction with the BLG or others for the targeted delivery type. And how to choose the lipid for the vehicle, and how to calculate using combination with if we using two or more of the lipid. And the last, maybe how about the purification using packaging, right? Using membrane cassette. How to choose the size of the membrane cassette for the purification of nanoparticles. Thank you.
Okay. Yeah.
Thank you. So we have three questions there. Inshallah, I will try to answer each and every one of them. So we start first with the selection of the type of market research, right? Okay. Now, as I mentioned previously, this is a lot of engineering, this is a lot of physics. So if you look at a commercial solution, basically a company that has already made from benchtop all the way to GMP level production, it's not necessarily that for each one of these solution or each one of these device, they have a specific type of research. For example, I know for a fact that in precision and system, they use benchtop. In their benchtop system, in lab of chip, they use target herringbone mixer. However, when you go up to the GMP level, they use toroidal because the idea is that it is more efficient that way. The problem with staggered herringbone mixer is that the longer that you use it, because remember it is a striation. When you have striation, you introduce turbulent flow and you also introduce some resistance to the flow itself. And the striation is like a cuboidal shape within the channel itself. Now, imagine if you have something that is cuboidal, that is not how to say it, like hydrodynamically fluent inside the channel. So you can have like every time you use it, you will get more and more corroded. Not corroded in terms of like rust and everything. It gets more and more erosion to the structure itself. Therefore, in toroidal, so each one of them is like a pillar inside the microchannel. Now, pillar is more hydrodynamically shaped, so it has less erosion for their design. However, when you compare the when they did the design and everything, they have to also make sure for their customers, which is us, client from industry, from research, they have to make sure that the design of the staggered herringbone mixer and design of the toroidal, at the end of the day, they are repeatable. What you did in benchtop, even though it's staggered herringbone mixer, and what you did in toroidal for the GMP level, it is the same as long as you use the same lipid, use the same temperature, and use the same flow rate ratio and total flow rate. So that is the design from the engineer himself. Okay, so that is one. And secondly, about the selection of lipid, right? Okay, selection of lipid. So now selection of lipid is a bit more complex because in my case, what I did was I used DSPC, DPPC, and DSPG plus cholesterol. These are three combination plus one cholesterol. The reason why I use this lipid is because, well, obviously, all of us researchers, what we do is we look at the literature and everything like that, right? So basically, there was one this paper saying that they used this before and it works. Now I chose this, and not immediately that it is you can use it directly according to what the composition that you read from literature. No, you have to adjust the molar or the formulation. Okay, so the molar composition you have to adjust. So can't remember exactly what because I have several formulation. I think I did about 15 formulation. The ones that actually work is formulation 5 and formulation 7, which have a different composition for each of them. However, this is all the trial and error part of the research itself. You have a starting point where this kind of lipid can encapsulate this kind of drug. Now, that is your starting point. So from there, you start adjusting the composition itself, the molar ratio and everything. And then you can also, from this 15 formulation, what I did also, I take out one part. I take out one lipid, or I don't replace it together. I replace the molar ratio from other part of lipid. For example, if the SPC, the PPC, and the SPG have 30 for each of them, so now total is 90, right? So if I take one of the lipid, for example, I take out the PPC, now the SPC and the SPG will have 45 ratio for each one of them, so to cover the composition. So these are all trial and error that you have to do from there, but you have to have a good starting point to justify the start point. Otherwise, yes, you can also take whatever it is and try, but that is not very scientific and it can get quite a long time to do it. But if you get a good starting point, start from there and then try to change the molar ratio and also the formulation itself. Okay, so that is about the selection of lipid. And thirdly, about the tangential flow filtration. Now, this filter, they are also like filter centrifugation. They have the molecular weight cut off, right? Okay, so now they are in kilodalton. Now, you have to look at what API you are using and what are the size of your liposome. Liposome, I can say very confidently that it won't pass through the membrane. That one is fine. That one is okay. Because what I did before, if you have one of these, I didn't have the video with me. What I did was I mixed dextran blue. Dextran blue has a very high molecular weight, dextran blue. And then I mix it with pyranine. Pyranine is yellow. Dextran blue is blue. So what happens if you mix blue and yellow? You get?
Yeah.
You get green, right?
Green.
So now the green, you put in that, and it's not clear liquid, but there's no precipitate or things like that, because it is a solution. So dextran blue is a solution, pyranine is also a solution. You put it together, and then this is what I did to test the cassette itself. So at the end of the run, you get back a blue and a yellow liquid from a green solution. It is really like magic, how you can separate two solutions. This is not suspension, this is solution. So you determine what is the size of the particles that you want. You determine the size of your API, and whatever in between should be flushed through the filtrate. Okay. So I hope that's answered the question.
Thank you.
Okay.
Okay, thank you. So any more questions, Pak Bambang? Or
Maybe want to know about the replacement for the BTC, the
the molar ratio or the flow rate ratio?
Yeah, molar ratio.
Molar ratio.
The maximum molar for the lipid for the formulation.
For the formulation.
Especially, for example, at my laboratory, I've seen 50 molar ratio for the lipid. Maybe you have experience.
Okay. As I mentioned previously, this is trial and error. So we have the start point and we do the trial and error. However, the trial and error for me, I use cholesterol as the marking point. Basically, I adjust the cholesterol, and then from there, I will divide it together with the SPG, the SPC, and also the PPC. So from there, because what I found is that the higher the amount of cholesterol, yes, it is good. You can get better PDI, you can get better form liposome and everything. However, this is later on in my research. When I try to freeze dry it doesn't work very well, because composition that has higher amount of cholesterol, it doesn't react very well with a freeze drying process. Because you have to remember, one of the things that I found, this is something that when you read publications, you have to think critically as well. This is I encourage master students and PhD students to think. When you read, you have to also to think. For example, there are some papers that claiming you can spin or you can ultra centrifuge this liposome up till how many thousands G, for example. Imagine this is a liposome. It is not a strong. It is not a cell. Cell have cytoskeletons which give them rigid. It's not rigid, but give them shapes. However, this is liposome. It doesn't have anything else. If you expose them to that high level of gravity, to the centrifugal forces, it will get squished. Now, the problem with the liposome is that once it gets squished, it has no capability to return back to normal because it is a membrane that can, it can get tangled to each other. The reason why I say this is because I also did some study with AFM, with liposomes. Now, when you did AFM with liposome, you have to dry the surface. So when it's dried, it is flat. Now the flat size of liposome versus the spherical size of liposome is different. So you have to think when you are looking at this kind of result in publish and everything, you have to think, this is a dried surface. And liposome doesn't have cytoskeleton. It is flat. It is like jellyfish on the beach. It's really flat like that. So when it does that, so the size is not normal anymore. Now, coming back to the freeze drying part, what I read in the paper saying that, okay, we just have to put in some cryoprotectant, and then it can protect the liposome itself during the process. Now, you have to remember, when you're doing buffer, especially in aqua solution, if you put in more components outside, for example, in this case, trehalose or sucrose or even protectant, you are increasing the osmotic pressure outside. So basically, you're pulling the water from inside the liposome out. So now the size is smaller. When you did that, if you check it back again, basically what will happen is that your size of the liposome will become smaller. And that will also impact during the freeze drying process. When you rehydrate it back, you'll find out why is it different. It's not different because of it's not cryoprotected. It might be because of that as well, because there's no, if you put the cryoprotectant outside, it doesn't have cryoprotectant inside the liposome itself. So during the process of the formulation itself, within the aqueous phase, you have to put in cryoprotectant. So cryoprotectant is inside the liposome as well. So now when I did that, I have to find a balance between the amount of cryoprotectant and also the let's say the cryoprotective effect, so that when I rehydrate it back, it doesn't expand. So there is a size, there is a specific amount of trehalose that I need to put in. However, what I found interesting is that with formulation with higher amount of cholesterol, it doesn't show the effect. No matter how much I put in the trehalose, it doesn't protect it. I suspect it because the cholesterol cannot retain the shape, even though you put in enough cryoprotectant. So the best point is start from the cholesterol. Maybe you give it until 50% of cholesterol. And then the rest, you divide it together with the lipid. And then you see from there. And also it depends on what is the range of size that you want. So if once you find it, and then you have to, once you have like, for example, 3 or 4 formulations, and then you try to encapsulate what you want. So these different formulation will have different encapsulation efficiency as well. So you have to select from them. But start from the blank one.
Okay, thank you, Dr. Taufik. So we still have about 30 minutes for this Q&A session. So I give you this opportunity to the students. We have a master program student doctor here. So I'm sure there are some of them working on nano. Yeah. So please use this opportunity to ask as many as you want. Yes. Somebody I will ask was it to push them for asking typical students. It's fine. It's simply quite hard pressed to ask my student to ask questions. So I believe that this is a shared trip between our Nusantara. So Asian students also like that. Quite shy to ask questions. And we are going to do that. But I believe that when I look to this, and there is a studying vision when I look at that. They are very proactive to ask questions. And there are questions that I so why do you want to ask them about the problems? Maybe some of you pharmacists. Yeah, I think yeah. Maybe you can ask about the how the pharmacists in Malaysia, how the nanoparticle technology in Malaysia, so compared to Indonesia, because it's a nanoparticle now, it's kind of a trend for a drug development. You should, if we are talking about the drug development. So if there's no question from the audience, maybe I will ask you a question. That's because I'm not, my background is not from nanotechnology. So, but this is always in my mind about the nanoparticle. Is nanoparticle the answer of all the problems that faced by, I mean, like compatibility or bioavailability? Usually, what I heard is that if your extract or your molecule cannot dissolve in water, for example, so change to nano, so becoming it can be like it can dissolve easier. I mean, like better than not using as a nano. So what's your opinion? What do you think about that? Maybe I'm wrong, but
This will be DCS class 3 and class 4 for the second, right? So um, when we are talking about nanoparticles, right? This is for someone outside of the field, or we're talking about this nanoparticle. Oh, this is a very advanced method and things like that. However, I would like to take it down a notch. Back when I did my PhD, a lot of people would look at this carrier. They say that, okay, you have a good carrier. Why not you encapsulate something that is really expensive? That all the MABs, for example, monoclonal antibodies, put in there, and then you try to make it more targeted. But my view as pharmacist, because this my education shaped me as well, because I work in Ministry of Health before. The problem that we have is not I would say it's not the amount or the variety of drug that we have. That is not our problem. The problem is that and this is not affordable. Our drug is not affordable. Simply that. So the research of liposome, for me, it is better suited if you use it to encapsulate or to send drugs that are old, but you can repurpose them so that it is more effective, it has less side effect, and it is affordable to the patient. For example, in my research, what I did was I encapsulated cisplatin and irinotecan. These are old drugs. Okay, these are old drugs. So that's why I mentioned. Someone said that, oh, why don't you use it for a really advanced drug? I said this actually deviate from the original purpose of this research, which is to make drug affordable. Now, when you are talking about whether this is a silver bullet to fix all of our problems, this really depends on how much advancement that we make in this field and to what end that we are using those advancements. For example, we do have lots of diagnostic that is really advanced because they have a specific targeting mechanism and they can send to a specific place. However, the key point, the limiting factor is this targeting mechanism, because even if you have a very good drug, but you have a poor targeting mechanism, even for the carrier or for the drug itself, then it doesn't work. So yes, you can use some part of it. For example, you are from your background is from natural product, right? So maybe some of these products they can get quite expensive to manufacture. Okay. However, if you give it in a raw form, it is toxic because it just go everywhere and infects everywhere. Now, if you put in liposome and you put in proper targeting mechanism, you don't have to purify it all the way down to a singular component, singular compound, but you can send it to the direct target, and then that will lower the cost because you don't have to go further in your purification compound. But at the same time, because of liposome itself, the liposome technology itself is mature, you can achieve economies of scale. So that, in that sense, it can be affordable to people.
Mhm.
So, as I mentioned, it's not a solution for all, but it is some solution. I guess.
Okay, yeah, thank you very much for so well, it enlightened me as well. It's like it's not uh the solution of all problems. Yeah. Okay. Before I continue, so is there any questions from the audience? So you can ask in bahasa Indonesia, bahasa Jawa, because he said that he can speak Java. So
Siti-siti ni.
ya, sithik-sithik. Ya, takon dhisik ya gitu ya.
Zek.
Takon. Atau pakai bahasa Melayu. Mas Yusuf ini kemarin yang ini ada salah satu student kita kemarin attachment di hospital di IUM ya, di hospital IUM. Gitu. Ya. Any questions dari audience? Maybe now we use gado-gado, bahasa gado-gado ya. I'm tired to speak in English actually. No, just kidding. Maybe Pak Hatta, is there any questions, Pak Hatta?
Yeah. Yeah, it's super interesting. Not only my because I work microfluidic, but not in production of my family. But I my research is about how to develop microfluidic to detect something or drug not only drug discovery but drug discovery. So that's why my question is maybe this one. Do you have in your laboratory to have a clean room and also how to say facility how to make a silicon paper or something like this? Because this one is very crucial for us to develop a new device for not only for detection but also for drug discovery and so on. Yeah, this one is technical.
It's fine. Thank you. Thank you for the question. So the question is whether in IUM we do have labs that can accommodate for basically creation or manufacturing of a silicon wafer in order for to get the chip itself, lab on the chip itself. Okay. Well, we don't have those. Okay. When I come back to Malaysia, okay, I think this is something that we experience it in most of the Asian countries. We do have ambition, we do have vision, we do really want to do things, but unfortunately, maybe the funding is still lacking. So we have to be honest with ourselves. Cannot do this. Okay. However, what we can do is to find connection of where we can go. I believe, to answer your question, USM does have some facility to create the wafer itself. I think they have a collaboration with their engineering department to create that. So maybe you can contact someone from USM. So we can talk later about this because I know that they are also doing that as well, the diagnostic part, but they are not doing towards the making liposome part. So they do have the collaboration with the engineering. However, what I'm doing to further my own research in this is to have a collaboration with NTU, Nanyang Technological University in Singapore. So they do have microfluidics lab for this liposomes and everything. So once we have a solid project and everything, so my student will go over there and they will do all the project over there in NTU. Because actually I asked every lab in Malaysia, they don't have the same microfluidic device that I worked in UK before and before, because as I mentioned, this is the issue of money. However, this is also as administrator in my kuliah, okay, as a deputy dean, we have to think about this as well. How to gain funding, how to gain these kind of things as well. So we have to be realistic. We have to know our limitations, and we have to reflect that in our work as well. Because what I would like to see, what I would like to talk with my students as well, is that if you do a work, if you do a research, and you know that this is the limitation of your work, just say that in your work, this you cannot do this. Because I saw that some of the students sometimes they, for the lack of better word, they embellish the fact. They embellish the fact, they pad the data and things like that. Which is for me, it doesn't help anyone actually. It doesn't have you. It doesn't have anyone else that might be referring to your work. So if you don't have it, just say you don't have it. If you have to jerry rig something, you have to just make something on the fly. Just say you make something on the fly, and you say what you did.
Yeah.
So once you say what you did, maybe other people can replicate that, and maybe get the same result, and maybe can further refine your work. So that's it. That's fine.
Okay.
So yes, that's to answer your question, Tata. Maybe you can collaborate with USM for that creation of the wafer, silicon wafer for this. But yeah, you don't have to scenario.
Yeah. Okay. So I think that's what we call the importance of collaboration.
Yeah.
Because we cannot, sometimes we don't have any facilities that we have like here or maybe in IUM, because I remember when I was back after my study in Australia, there is no HPLC here or something like that. I was quite, oh, what I'm going to do. So there's no NMR or something like that. So so this is the importance of collaboration. So I think the work is about collaboration. It's not by ourselves. Okay. So is there any more questions for the audience? If there's no questions, I would like to, because we still have about 15 minutes, so I would like to use this really good opportunity because um, this is actually, because it's not my expertise as well. We are talking about liposome, yeah, and I heard that now it's a kind of a trend using liposome for nanoparticle or something like that. Is it liposome is like a carrier for in this kind of a nanoparticle? Is that
Yes,
liposome
it
is
is a,
carrier?
it's a carrier. It's a type of carrier within the nanoparticles.
Okay, it's a carrier. So, and so what is the advantages of using liposome, or is that this, what is the disadvantages using liposome? I mean, is there any limitation of using a liposome?
Okay, so basically, yeah, to recap that question back again, liposome is one type of nanoparticles. We do have lots of them. And I think every year someone somewhere will come up with really clever method of using magnetics, using acoustic, lots of things. They are really, really clever people. So, however, as I mentioned previously, the issue is that these methods, however clever they are, they still do require clinical trials. You have to test it, everything. Now, one of the advantages of liposome is that because it has been around for so long, we have lots of body of work on it. So we have lots of sources of knowledge that we can draw from. So some of them has already gone to clinical trial, approved as a product and things like that. We can use that as a baseline to create new products. So once we have a new drug, the subsequent drugs are easier. For example, if you look at antibiotics, you have cephalosporin, right? So cephalosporin, first generation, okay, this is the first one. So they do have to go through all the testing and everything. However, when you go to second generation cephalosporin, third generation cephalosporin, these are just the manipulation of side chains. They already know what the main chains are doing. So the manipulation of side chains just whether improve or deteriorate the function of the antibiotics. So basically, you can say that these are no longer effective against gram-positive bacteria. So these are better against gram-negative bacteria. So your body of work has already there. So for liposome, for example, that is the advantage. Your body of work is there, the experience are there, the policies and guidelines are there, so it's easier. However, in terms of shortcomings, okay, one of the second advantage is that liposomes are made from lipid that can be found within ourselves. Phosphatidylcholine, for example, PC, they can be found in egg yolk, they can be found in our lung as a expectant, because these kind of things are there in the body. So it's not saying that it is inert. Our body can still use it to a certain extent. However, it is not foreign to the body in the sense that, for example, if you put gold in your body, that is foreign. If you put magnetic ferrite within the body, that is foreign. So this one is not foreign. This is your body produces it as part of the cycle, as part of the metabolism. So that is another advantage. The disadvantage of this is this: the loading capacity. Okay, now maybe some of you who work in the nanoparticles and this liposome work, you might find hundreds and thousands of papers that are claiming their encapsulation efficiencies are 98%, 99%. Now, some of these are just manipulation of numbers. That's it. So that's why when you are reading something, you have to think about what did you just read? Is this true? 98%. It is something like this. When you are creating a liposome, imagine the carrier itself has to be constructed from the lipids. So for example, let's say you have 1,000 lipids to create one liposome, for example. Okay. Now, in order for it to have a full amount of drug inside that, you have to have 100 drugs inside the liposome itself to fill the liposome. So if you say that you get almost 100% encapsulation efficiency, that means you know exactly how much molecules of lipid you put in. For example, if you want to make 4, you have 4,000 lipid inside that solution, and you have 400 API, and all of them happily form liposome together without any imperfection, and all of this API is included inside 100 for each of liposome, which is for me is a fantasy. It is fantasy. So we have to contend with the fact that the production method, the manufacturing method is not perfect, but it can be improved by manipulating the amount of lipid that you put in, by manipulating the API that you put in, because one of the disadvantage is the encapsulation efficiency. It is quite low. Some of them gets 20%, 30%, 40%, because we have to know, if we put in more lipid, yes, we can have more liposome. However, you have to put in more API to fill in those liposome. So you have to find a good balance between the amount of the lipid to form the liposome and the amount of API to feed that in. And that's where the flow rate ratio and total flow rate comes into play. Because the faster that you make this flow, there's not enough time for the API to get inside the liposome as well. And this is not saying that the drug, oh, I must find the inside of the liposome. No, it has to come naturally through concentration, gradient, and things like that. So that is the disadvantages. However, with more and more technological advancement, we can get a better encapsulation efficiency in the future.
Okay, thank you. So, still any questions, maybe? Before I close this session for this morning, I have one last question for you. Related to our topic today, what is the biggest challenge to scale up this kind of nanoparticle into industry, and also bring this from lab into patients? So, yeah.
Thank you. So I believe the biggest challenge is actually regulatory. Okay. Because of this, everyone is scared of new things. We look at COVID-19, we are scared of the virus, we got scared of the vaccine as well. Everyone always have a reason to be scared of things. And this is the same thing for government as well. And you have to contend with the fact that governments are always political. So every time you have something new coming in, and they have to take into account all the sound, all the voices, all the opinions from all the people. And these people are not necessarily expert in their field. They can give some opinion, and then they can get some traction in some social media and things like that. And then the government will think that, okay, we need to put extra precaution into this, or we need to maybe lessen the regulation on this. So these kind of things happen. We have to face the reality that it happens. Therefore, the main challenge is regulatory, of which that for each country, it's bad enough that we have different regulatory requirement for each country. BPOM-RI with NPRA are different. So BPOM-RI, they have their own selected requirement to pass certain medication in Indonesia. NPRA also have certain requirement to release the same medication in Indonesia. Okay, so even though we are from the same region, we are basically the same people. So there is not much um, ethnicity differences between us. However, when it comes to regulatory, to the liposomes and everything, usually when the government is concerned, I'm using the word concern rather than fear, to scare, they will ask for more and more tests. When you ask for more and more tests, you ask for more and more verification, these are all costs. They are not cheap. So when they are not cheap, that becomes harder and harder for businesses to invest into this, because they have to think, if we invest in this, what is our market? Is this something that can be accepted by the market? Can we gain something else from the medication? I'll give an example for this. You know about Ozempic? Anyone heard about Ozempic? All of us pharmacists, we should know about Ozempic. Ozempic is a diabetes drug, right? But what is the secondary use of it? Weight loss, right? So Ozempic actually has been used by the celebrities in Hollywood to lose weight very, very fast. And now they are the ones that are promoting to people that this works. Now, these companies, they know that they can have a secondary income from this, but it has to pass through regulation. FDA has to pass through this, say that this works for weight loss, then they can market it. But that is in the US. They might send it to another country that has lower and lower regulation, and they can benefit from that as well. Because our world is interconnected. We see something happening in the US. If we can get Ozempic here in Indonesia, or in Indonesia, for example, then we might use it as well, if we don't have a proper regulation for that. Now, these businesses, they are looking into that as well. If they can make money from it, they don't care about the test and everything. But if they cannot make money from it, then the funding will become the problem. So it starts from the regulatory, and then it goes to funding, and then at the end of it, it will be affecting us as well.
Okay, thank you, Dr. Taufik. It's really interesting talking about the challenge, about the funding, about the regulation. So, yeah, I think with that, if there is no questions, so I think once again, give a big applause to Dr. Taufik for his sharing today. All right. Before closing this session, I think I would like to ask maybe Hatan to give the. Oh no, sorry. Yeah. Oh nggak ada. Okay. All right. Sorry. There's no coordination before maybe. All right. So I will not give a conclusion or something like that. I think everyone here can make their own conclusion about this liposome. So to end this program, once again, thank you very much, Dr. Taufik, for sharing your knowledge here in this program, guys, and hopefully it will give kind of a knowledge for us, or also for the students here and the audience in the YouTube or the Zoom. All right. To close this, guys, this well, it's almost afternoon here. We recite Alhamdulillah here. Alhamdulillah Rabbil Alamin. Thank you once again for your attending here, and thank you. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, Dr. Oh, ada. Gimana? Ini, Ustaz. Ada. Oh. Okay. There's a token of appreciation for our department, so I would like to ask Dr. Taufik to come forward. Yeah. And also, I would like to ask Pak Atan maybe to give the token of appreciation to Dr. Taufik. So, the photographer, please, to document this. Ya. Oke, terima kasih Dr. Taufik and terima kasih dan sekali lagi applause to Dr. Taufik. Thank you. Untuk presentasi minat programnya sekarang ini. Kok saya yang ini? Langsung diminta ini aja. Masih gimana? Diminta untuk mempresentasikan. Loh, saya nggak tahu ya. Kira ini mahasiswanya udah tahu? Sudah. Oh gitu. Diminta. Oh. Oke, ini ada pesan dari itu untuk mahasiswa yang mau seminar terbuka. Silakan. Ini tadi gimana? Saya tidak tahu bahasa. Saya tiba-tiba gitu. Oh iya, silakan yang. Iya. Saya di sini berfungsi sebagai apa? Oke, silakan mungkin Mbak Martania, iya yang akan melakukan seminar terbuka di sini. Aku terus ke sudah. Aku sudah enggak. Oh, sudah. Terus yang megang kendali siapa nanti? Ibu sudah. Oke, thank you. Oke.
Oh, bisa berjalan. Nah ya, HP-nya udah punya HP masuk.
Yes.
Ini di dulu. Di mana? Di mana?
kecepatan MS sampai yang ini tahu saya ini ini kenapa pakai Martania, dokumen Martania dulu. Masih itu langsung ya?
Bapak duduk aja.
Duduk aja ya. Ini langsung. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih saya ucapkan kepada Ibu Asi atas semua dukungan dan kesempatannya pada hari ini sehingga saya ada di sini. Dan terima kasih juga kepada teman-teman semua yang sudah bisa hadir pada acara KAIST pagi ini. Di sini saya ingin memaparkan hasil tesis saya yang berjudul Analisis Kepuasan Pasien Terhadap Penerapan Telefarmasi di Apotek. Kenapa saya menetapkan hasil tersebut? Kenapa saya menetapkan judul tersebut? Karena di sini seiring terjadinya pandemi COVID-19 secara nyata telah menimbulkan hambatan serius pada pelayanan kefarmasian yang notabene-nya membuat mobilitas masyarakat itu menjadi terhambat karena adanya kebijakan pemerintah yang disebut dengan physical distancing. Nah, di sini pelayanan telefarmasi menjadi salah satu solusi. Namun kalian perlu tahu bahwa bagaimana gambaran kualitas dan kepuasan konsumen itu sendiri terhadap pelayanan telefarmasi. Sebelum kita mengetahui apa saja sih kegiatan dalam pelayanan telefarmasi itu, kalian harus tahu dulu telefarmasi itu sendiri. Jadi di sini definisi dari telefarmasi itu sendiri, pertama dari Permenkes nomor 14 tahun 2021 dan National Association of Board of Pharmacists, di sini menjelaskan bahwa telefarmasi itu merupakan suatu pelayanan kefarmasian yang dilakukan oleh apoteker di mana melalui penggunaan teknologi dan telekomunikasi dan sistem informasi kepada pasien jarak jauh. Nah, di sini kita bisa lihat beberapa konsultasi yang dilakukan oleh beberapa apotek menggunakan pelayanan telefarmasi. Di sini satu ada pembelian obat. Jadi ada beberapa pasien yang menggunakan pelayanan telefarmasi itu, contohnya dia meminta obat, dia memesan obat melalui WA. Nah, kemudian nanti dari pihak apotek akan mengirimkan obat itu sampai ke rumah. Dan lainnya adalah pasien akan menanyakan bagaimana cara penggunaan obat. Jadi di sini respon apoteker itu benar-benar harus bisa memahami atau bisa memberikan solusi dari pertanyaan pasien. Contohnya kita lihat di sini adalah sirup-sirup pemberi rasa yang nantinya bisa dicampur dengan puyer. Nah, ini udah agak lama. Nah, pasien ini menjelaskan masih bisa nggak digunakan untuk mencampur puyer tersebut. Nah, jadi di sini apoteker harus berperan dalam bisa menjawab solusi untuk penanganan tersebut. Kemudian di sini juga ada lagi selain ada penggunaan obat tersebut, ada lagi konsultasi pasien. Jadi pasien juga dalam pemasarannya itu di apotek itu kadang ada yang konsultasi, jadi nanya pasien ini seperti ini. Nah, di sini contohnya itu pasien tuh gatal. Nah, bagaimana sih apoteker ini bisa memberikan solusi untuk atau pilihan tepat obat yang sesuai dari apa yang dialami oleh si pasien tersebut. Dan terakhir di sini juga ada penggunaan obat. Pasien menanyakan apakah inhaler ini bisa digunakan kembali atau diuji ulang kembali, dan di sini apoteker pun harus bisa menjawab. Nah, jadi beberapa pengalaman yang dilakukan melalui telefarmasi itu tidak hanya melayani obat aja, tetapi juga di sini pasien juga menginginkan adanya pemahaman lebih lanjut mengenai cara penggunaan obat, mengenai konsultasi obat yang dirasakan pasien itu sendiri. Nah, untuk mengukur suatu kepuasan pasien, maka dalam pelayanan telefarmasi itu kita harus memahami dimensi yang ada di dalamnya. Dimensi apa? Yaitu dimensi mengenai kualitas pelayanan. Karena dimensi kualitas pelayanan ini saat kita terapkan dalam pelayanan, maka akan membentuk suatu kepuasan pasien. Nah, kepuasan pasien ini kita bisa artikan secara sederhana menurut Ismono, yaitu keadaan di mana kebutuhan, keinginan, dan harapan pasien ini dapat terpenuhi melalui produk ataupun jasa yang sudah dia dapatkan. Indikator dalam pembentukan kepuasan. Jadi saat pasien itu sudah mengalami puas, maka kita bisa lihat indikatornya. Yang pertama yaitu pasien akan merasa di mana harapannya itu sesuai dengan yang diterimanya. Jadi kenyataan itu sama, sesuai. Apa yang diinginkan dia itu sama dengan harapan dia. Itu pertama. Yang kedua, minat berkunjung kembali. Artinya pasien itu akan menjadi suatu pelanggan tetap. Jadi dia akan datang lagi, dan datang lagi. Dan yang terakhir indikatornya kita lihat bahwa pasien itu akan memberikan suatu rekomendasi. Jadi pasien ini akan menjadi promosi utama. Jadi dia akan, kalau dia merasa puas, maka dia akan menceritakan ke teman-temannya, ke masyarakat lain. Nah, sehingga pasien itu merupakan salah satu promotor terbaik. Nah, di sini kerangka konsep dari penelitian saya itu, pelayanan telefarmasi ini diukur dari 5 kualitas dimensi tadi, kualitas pelayanan itu. Nah, kualitas pelayanan ini akan menimbulkan suatu tanggapan pasien. Pasien itu tanggapannya puas atau tidak puas. Nah, tanggapan pasien ini bisa disusun atau didukung dari 5 dimensi menurut Parasuman, Zainit, dan Berry dalam Ciptono tahun 2015 ini ada changeable, reliability, responsiveness, assurance, kemudian ada empati. Dan berikutnya juga kita bisa lihat dari media sosial, yaitu cuitan netizen dari Twitter. Nah, keduanya kita bisa lihat bahwa pasien itu merasa puas atau tidak. Untuk metode penelitiannya ini yaitu rancang pantang lintang yang merupakan penelitian kuantitatif dengan metode survei di mana mengikuti non-probability sampling. Data yang kita gunakan kuesioner yang kita bagikan kepada responden, di mana untuk kriteria inklusinya itu responden yaitu pasien yang pernah mendapatkan pelayanan telefarmasi di apotek. Kemudian pasien ini umurnya kita jarakkan antara 18 sampai 65. Kemudian pasien ini apotek yang kita gunakan adalah apotek yang ada di wilayah Sleman. Dan untuk eksklusinya ya ada beberapa pasien yang tidak menyelesaikan kuesioner dengan baik ataupun pasien yang tidak bisa mengisi kuesioner ataupun data yang kita kirimkan. Nah, untuk data sekundernya itu kita ambil dari Twitter, cuitan Twitter dengan kata kunci pelayanan apoteker online, obat online, apotek online, dan beberapa lainnya. Untuk variabel, sampel, kriteria, dan tahapan penelitian di sini, untuk variabelnya kita dibagi menjadi ada profil pasien, kemudian kepuasan pasien, ada populasi dan sampel. Profil pasien, untuk survei pasien, di dalam kuesioner ini ada jenis kelamin, usia, pendidikan, pekerjaan, dan frekuensi pasien itu mengakses telefarmasi. Kemudian kalau dari segi sosial media, kita lihat dari sentimen atau tanggapan si pasien itu baik, buruk, ataupun netral. Kemudian kita lihat dari aspek hukum, aspek obat, aspek resep. Kemudian kepuasan pasien kita lihat dari 5 dimensi kualitas. Dan dari media sosial ada aspek pelayanan, aspek pengiriman, aspek teknologi, dan aspek apotik. Untuk populasinya, ini pasien yang pernah mengakses pelayanan telefarmasi. Nah, media sosial yang kita pakai ini adalah Twitter. tweet yang diambil dari Twitter yang terkait tentang telefarmasi itu. Kemudian sampelnya ini pasien yang pernah mengakses pelayanan telefarmasi di apotik berusia 18-65 tahun, kemudian apotik yang ada di wilayah Sleman. Nah, kemudian di sini tweetnya yang diambil dengan kata kunci obat online, apotik online, pengiriman obat ke rumah, informasi obat, dan lain sebagainya. Cara penelitiannya di sini pertama-tama saya melakukan pengumpulan data mengenai informasi tentang telefarmasi dan kepuasan pasien di apotek. Lanjut berikutnya, saya membuat suatu kuesioner dengan indikator penilaian. Nah, untuk membuat suatu kuesioner itu kita lihat butir kuesioner itu harus sesuai dengan indikatornya. Indikatornya itu yang kita buat dari 5 dimensi untuk pengembangan 5 dimensi kualitas pelayanan. Nah, sehingga nanti di sini kepuasan pasien akan terlihat dari penilaiannya, yaitu dari 5 dimensi tersebut. Kemudian kuesioner itu kita uji di sini, uji kuesioner yang pertama yaitu kita menggunakan para pakar. Jadi untuk melihat isi dari konstruk ataupun isi dari kuesioner tersebut. Nah, setelah itu kita uji dengan SPSS untuk melihat adanya kevalidan ataupun keabsahan dari kuesioner tadi. Nah, kemudian setelah dari para pakar kita buat uji kembali pada beberapa forum, yaitu forum pasien yang pernah menggunakan telefarmasi di satu apotek yang ada di Sleman. Nah, itu untuk melihat pemahaman sampai mana pasien ini bisa menjawab atau memahami kuesioner yang saya berikan. Nah, terakhir adalah uji SPSS untuk menggunakan kuesioner tadi, sehingga nantinya kuesioner yang sudah benar-benar valid dan reliable ini kita bisa bagikan untuk uji hasil. Di uji hasil ini kita menggunakan analisis IPA, sehingga kita bisa menentukan hipotesa yang sudah kita susun. Nah, berikutnya kuesioner tadi kita bagikan kepada responden 100 responden yang ada di wilayah Sleman, apotek-apotek yang Sleman. Dengan ini menggunakan WA. Jadi kita melalui WA grup yang ada di apotek-apotek itu kita sebarkan dengan Google Form. Nah, kemudian data mining ini untuk mengambil tweetan Twitter. Kemudian hasil ini nantinya kita lihat bahwa pasien itu merasa puas atau tidak, sehingga hipotesis itu akan terjawab. Nah, langkah penelitiannya di sini tadi kita jelaskan bahwa kita pertama melakukan keabsahan dari instrumennya. Kita buat instrumen dulu, kita buat kuesioner dulu, yang kemudian kita uji validasi instrumennya, kemudian kita lakukan analisis data miningnya. Nah, hasil penelitian pembahasan. Pengembangan instrumen dan alat uji. Yang pertama kita lakukan tadi, udah kita jelaskan bahwa kita melakukan uji validasi isi dulu, kita menggunakan 7 pakar untuk melihat konstruknya, isinya sesuai atau tidak dengan indikator yang diberikan. Nah, untuk penilaian isi ini, para pakar akan menjawab dengan kriteria penilaian skala 4. Jadi, skala Likert 4 ini menurut Sugiono tahun 2015 dia di situ dijelaskan bahwa kriterianya kalau nilai 1 itu artinya bahwa nanti para pakar akan menjawab kalau si butir kuesioner yang dibuat itu tidak akan sesuai dengan indikator. Kemudian kalau nilainya 2 artinya ada mayoritas atau kesalahan banyak dari kuesioner atau butir soal yang kita buat. Kemudian kalau untuk yang nilai 3 itu kalau misalnya revisinya itu sedikit, artinya soal yang kita buat tidak terlalu banyak revisiannya. Dan yang keempat, nilai 4 itu apabila si soal ini sesuai dengan indikator yang sudah kita buat. Nah, kemudian kita lakukan FGD atau uji validasi yang kedua untuk memahami sebatas mana pasien bisa memahami instrumen yang kita buat. Dan yang terakhir kita melakukan uji SPSS untuk melihat alat yang kita gunakan atau kuesioner yang kita buat itu benar-benar valid dan bisa kita gunakan sehingga jawaban pasien itu tidak antara jawaban sekarang, besok ataupun nanti itu akan sama, tidak akan merubah jawaban. Nah, kemudian di sini yang kedua, kita melakukan analisis kepuasan pasien yang dilihat dari tingkat harapan dan kenyataan dari 5 dimensi. Di 5 dimensi ini ada assurance, reliability, tangible, kemudian ada responsif dan responsibilitas. Dan empati. Ini maaf, bukan responsibility tetapi adalah empati. Nah, kemudian yang terakhir adalah analisis kepuasan pasien dari segi media sosial. Dari segi media sosial itu adalah kita ambil dari Twitter dengan keyword ataupun kata kunci apotek online, apoteker online, pio online, dan tadi udah disebutkan banyak. Kemudian di sini analisis dari tingkat harapan dan kenyataan pasien atau 5 dimensi itu kita menggunakan analisis IPA atau Important Performance Analysis. Nah, Important Performance Analysis ini dia nanti tujuannya untuk mengukur tingkat harapan dan kenyataan yang diterima oleh pasien. Di sini kita menggunakan ada gambar diagram Kartesius. Hasil dari penelitian saya ini diagram Kartesiusnya menunjukkan di posisi B, artinya pertahankan prestasi. Pertahankan prestasi itu artinya harapan dan kenyataan itu udah sesuai. Atau apa yang diinginkan pasien itu harapannya sama dengan yang diharapkan oleh pasien. Dan kemudian perhitungan dari nilai skala intervalnya itu kita menggunakan Likert 4. Nah, di sini ranknya itu kita bisa hitung dari nilai skala dikalikan jumlah responden dibagi nilai tertinggi dikali jumlah responden, sehingga di sini kita lihat bahwa nilai 1 itu nanti menunjukkan tidak puas, berapa nilainya itu interval 0 sampai 25. Kemudian skor nilai penilaian 2 itu tidak puas, itu nilainya 26 sampai 50. Kemudian nilai puas itu nilainya 3, 51 sampai 75, dan sangat puas nilainya 4 sampai nilainya 4 di mana ranknya 76 sampai 100. Analisis kepuasan pasien dari 5 dimensi, kita lihat bahwa responsifnya itu menghasilkan skor 100%, intervalnya 76 sampai 100% yang menunjukkan bahwa tingkat kepuasannya itu sangat puas. Reliability-nya juga sama, di mana nilainya 9,914%, 76, ranknya 76 sampai 100%, dia juga sangat puas. Kemudian assurance-nya juga skornya 98,58%, intervalnya 76% sampai 100%, dia juga menunjukkan sangat puas. Tangible juga sama, 97,21%, interval ranknya 76 sampai 100%, dia juga menunjukkan sangat puas. Dan empati juga sama, 97,73%, dia ranknya 76 sampai 100, sangat puas. Maka pelayanan yang memuaskan akan membuat pasien setia untuk tetap menggunakan jasa yang diberikan. Pelanggan yang loyal akan membuat suatu intensif pemberian pelayanan kesehatan maupun mampu untuk bertahan. Nah, kemudian di sini analisis kepuasan pasien yang dilihat dari sosial media. Jadi saat kita mau melakukan analisis sosial media, kita mengambil cuitan netizen itu dari bulan Desember tahun 2022 sampai Maret 2023. Nah, kemudian hasil dari cuitan itu kita web sharing sejumlah 2.560 Twitter, dan kemudian kita lakukan cleaning sehingga kita dapatkan 1.274 tentang pasien yang berkomentar tentang telefarmasi. Nah, kemudian kita lakukan label atau kita melakukan poin penamaan di mana yang meliputi 5 dimensi tadi. Ada yang tangible, ada yang responsif, ada yang kemudian assurance, ada yang empati. Nah, dari beberapa 5 dimensi tadi, kita melihat dari aspek yang mewakilinya, itu ada aspek pelayanan, aspek obat, dan teknologi. Kenapa saya bahas kenapa saya membahas hanya 3? Karena 3 data ini adalah 3 data terbesar dari analisis yang saya dapatkan. Nah, teknologi, pelayanan obat, dan obat ini mempunyai nilai dari periode Januari sampai Juni 2020 sampai periode Juli Desember 2022 mempunyai rata-rata 90 sehingga dinyatakan bahwa pasien itu merasa puas. Nah, untuk teknologi ini dalam dimensi 5 kualitas, dia masuk ke dalam dimensi tangible dan pelayanan ini masuk ke dalam 5 dimensi pelayanan. Jadi ada tangible, ada assurance, ada empati, ada responsif, ada reliability, dan terakhir ada obat. Di sini aspek obat itu mewakili dari tangible dan asuran. Nah, kemudian di sini dari hasil yang saya dapatkan bahwa penggunaan layanan telefarmasi ini di apotek menjadi lebih efektif dan lebih efisien sehingga bisa dapat meningkatkan omset penjualan dan memajukan dari usaha itu menurut Nasution dan Badwawi tahun 2016. Nah, penggunaan layanan telefarmasi ini dari tahun ke tahun semakin meningkat dan di sini kita lihat bahwa peningkatan telefarmasi itu sangat tinggi pada tahun 2021 yaitu pada puncak saat terjadinya COVID. Dan setelah terjadinya COVID pun pelayanan telefarmasi masih kita gunakan sehingga di sini kita lihat adanya perkembangan teknologi itu membantu adanya layanan telefarmasi sehingga suatu perusahaan itu bisa meningkatkan dari pendapatannya. Peningkatan bisnis apotek online ini semakin tahun itu semakin meningkat, khususnya selama pandemi COVID. Pada tahun 2021 ini transaksi apotek online itu sangat tinggi sekali. Nah, di sini dijelaskan pada jurnal yang didapatkan oleh Halkam 2022 menyatakan bahwa telefarmasi sangat membantu masyarakat di masa pandemi dan setelah pandemi. Masyarakat masih menggunakan layanan telefarmasi. Masyarakat ini sangat bergantung dengan telefarmasi sampai sekarang. Berdasarkan data asosiasi penyedia jasa internet Indonesia, saat ini di Indonesia dari total jumlah penduduk sebanyak 2.560 juta, di antaranya pengguna Twitter, di sini mengalami kenaikan angka per tahunnya mulai dari 2004 sampai sekarang, bahwa sekarang tahun 2022 itu menunjukkan 13,8 juta jiwa masyarakat itu menggunakan telefarmasi ataupun menggunakan jasa internet untuk mencari masalah tentang kesehatan. Hal ini semakin memperkuat hasil penelitian saya bahwa kepuasan pasien itu terhadap pelayanan telefarmasi di apotek sangat baik. Mungkin dari saya ini ada kesimpulan dan saran. Yang pertama, kesimpulannya bahwa kuesioner yang saya buat itu valid dan benar. Dan yang kedua, kepuasan pasien di apotek, baik itu menggunakan kuesioner maupun media sosial dari 5 dimensi kualitas pelayanan menyatakan sangat puas. Dan saran dari saya, diharapkan penelitian berikutnya bisa menggunakan sosial media yang lain, baik itu ada Facebook, mungkin juga bisa dari e-commerce ataupun dari Instagram, dan berikutnya adalah untuk penelitian berikutnya dapat melihat atau mengukur pengetahuan apoteker. Terus yang berikutnya lagi mengukur persepsi masyarakat terhadap penelitian pelayan telefarmasi yang dilakukan oleh apoteker. Mungkin dari saya cukup sekian. Saya banyak berterima kasih pertama kepada pembimbing saya yaitu Ibu Suci Hanifah, kemudian yang kedua Bapak Domas Hatta, dan kemudian pada penguji saya yaitu Dr. Uma, kemudian pada Ibu Dwi Endarti dan staf program prodi farmasi Magister Farmasi UII, terutama Ibu Asi dan Mas Wahyu, dan karyawan saya yang ada di apotek, baik itu Apotek Murah Sehat dan Apotek Pahe, dan teman-teman Magister Farmasi tahun 2021. Terima kasih untuk semuanya atas dukungannya. Assalamualaikum warahmatullahi wabarakatuh.
Mana? Ambilin.
Sini.
Ini
Kena.
ya.
Iya.
Bagian lulusan pertama magister farmasi ya, maksud banget ya. Ya, terima kasih ya Mbak Martin ya.
Sama-sama Ibu.
Ya, semoga sukses ke depannya juga memicu teman-teman yang lain untuk segera lulus.
Baik.
Ya. Sip. Oke. Lain kita tunggu ya. Oke.
Satu Mas. Udah kan? Udah. Terima kasih atas semuanya Ibu-ibu. Udah. Selesai kan?